Hello everyone, my name is Kathan and today we'll be discussing the problem Chessboard and Queens from the Introductory Problems of the CSES problem set. Let's begin. So let me read out the question for you. Your task is to place 8 queens on a chessboard so that no 2 queens are attacking each other. As an additional challenge, each square is either free or reserved and you can only place queens on the free squares. However, the reserved squares do not prevent queens from attacking each other. Fine. So like the reserved square is not a blockage. So a queen can attack through that reserved square. That's what it means. How many possible ways are there to place the queens? The question is pretty simple. You are given a chessboard here, which will be of size 8 cross 8. If you don't know, like a chessboard typically has 64 squares, and you have to place 8 queens here in such a way that no 2 queens are attacking each other. So your task is to place 8 queens on a 8 by 8 chessboard such that no 2 queens attack each other. Fine. So your task is to find out how many total this possible ways are there. So how many total combination of 8 queens are there such that they don't attack each other on a chessboard, or you can say how many placements of 8 queens are there such that they don't attack each other on a 8 by 8 chessboard. Fine. So that's the question. Our input is simply 8 lines. So our input is simply a chessboard here, right? 8 by 8. So there will be 64 entries here. Each square is either free or reserved. So reserved means you cannot put a queen there, but a queen can attack through that square. If you don't know how a queen attacks, is a queen attacks in every possible direction. Like a queen can attack, you can say, in its column, in its row. So a queen can attack, you can say, row, column, or every possible diagonal. So queen, you can say, is the most powerful piece of a chessboard. And the reserved square means you cannot place a queen here, but a queen can attack through it, right? So if you put a queen here and a queen here, they will attack. That's what it means. Output is print one integer, the number of ways you can place the queen. So there are here 65 combinations, right? So that's what you have to do. So I guess the question is pretty straightforward. You have to place 8 queens on an 8 by 8 chessboard in a way that they don't attack each other, and you have to count how many ways are there. So yeah, I mean, that's about the question. And the challenge is there will be some reserved cells. This is why this number will keep on changing. So what I will do is I'll solve this problem as a general problem. Let's say you have a general problem of putting n queens on n by n chessboard. If we can solve that problem, this problem is automatically solved, right? So let's just go to the iPad and try to understand this question a bit more. So the problem given to us is actually about 8 by 8 chessboard. And what we have to do is we have to place 8 queens on it such that they don't attack each other. And if you don't know how a queen attacks, let me just show you how it attacks. Let's say this is your chessboard, some part of chessboard. If you place a queen here, this queen is going to attack in every possible direction. So a queen can attack here, queen can attack here, 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 and basically in 8 possible directions a queen can attack. Fine. So that's about how a queen attacks. The question says you find out how many ways you can place this 8 queens on this chessboard such that no 2 queens among these 8 attack each other. Now what I will do is I'll reframe it as let's say we have n by n chessboard, and I'm gonna try to place n queens on it. Right, so the problem is same. I'm just generalizing it. So if we can solve for this, this can be easily solved. And what it effectively means is your n will never go beyond 8. Right, so n will never go beyond 8. So automatically you can say n is very small. So you can try brute force enumeration. That's what it means. Fine. So two things. They are asking us to solve for this guy. You have to place 8 queens on 8 by 8 chessboard, but I'm gonna solve it for n queens on n by n chessboard where n doesn't go more than 8. So n is very small. It means we can do a brute force enumeration. We'll analyze the time complexity later on, but that's what I'm saying. You can think about brute force. Fine. So let's approach this question then. For now, forget about the reserved cells. The reserved cells we can handle, right? So what if there is a reserved cell? There's just one constraint. You cannot put a queen on it, but a queen can attack through it. So for now, question is very simple. We have a n by n chessboard, and we have to place n queens on it such that they don't attack each other. Fine. So how do you approach this question? Now what do you know about queens in a chessboard? So let's just write out the observations step by step. A queen can attack in 8 possible directions, right? So if you put a queen here, it can attack in 8 possible directions. So it says if it can attack in 8 possible directions in a row, you cannot have more than one queen. Fine, so like that's a very simple observation. Maybe I can write the queen here, the most powerful piece of a chessboard. I'm no chess expert, so don't fact check me on that. I don't know if it's actually true, but from what I can see, a queen can attack in 8 possible directions, so it might be the most powerful piece of the game. Fine, so it automatically says if it attacks in all the possible directions in a row, you can at max have one queen, right? So only one queen per row. Fine, only one queen per row. Fine, it also means only one queen per column, so only one queen per row or column. You can say row and a column. There can be only one queen per row and a column, and any of the diagonals. But I guess row and column, like since we have a matrix, right? So since we're dealing with n by n boards here, that's why I'm thinking in terms of rows and columns. So I might get some idea here what to do. Fine, so we have an idea that in a row there can be only one queen, and in a column there can be only one queen. Fine, so what does it say? Does it give you an idea that maybe what you can do is let's have a grid here. Let's say there's a grid. I am dealing with a 4x4 chessboard here. In this chessboard, it's a 4x4 chessboard, so we have to place 4 queens. 4 queens have to be placed. You can only place, let's say for a given column here, queen in one of these cells only. If a placement is valid, then only one of these 4 cells will have a queen, right? For example, in this row, only one of these 4 cells will have a queen. Fine, so what does it say? Like, does it give you a hint of how to enumerate, or you can say all the possible placements? Just think about the dumbest possible manner, right? So what you have is you have this 4x4 chessboard. You know this, you can only have one queen per row and a column. How can you go about placing queens in a way you can generate all the possible combinations of placements? Just think about pure brute force. Can you think? If not, I'll just try to give you, you can just steer you in correct direction. See, I know that in this column, I can only have queen in one of these locations, right? So let's say I have a queen in this location. Fine. Then what I can do is I can move to the second column. Now how many positions do I have to consider? I have 4 to consider, but out of these 4, only one, like there won't be all the valid placements. So this, like this are clearly not valid, so you only have one option here. Similarly, for this placement, you will have 4 total options, but only one of them you have to consider. In other words, what I'm trying to say here is for the 0th column, you have 4 ways to place the queen, right? So you consider all of them, fine. Then you move to the second column. Now, depending on what you chose here, try to make a choice here, right? Then you move to the second column or the column with index 2. Depending on all the combination of choices you made in this 2, so let's say there were C1 ways here, and let's say there were C2 ways here. Now for all the C1 into C2 ways, you try to make a choice here, right? Let's say there were C3 possible options. Depending on C1 into C2 into C3 choices, you try to make choice here, right? So what I'm saying is, you go through all the columns one by one. So let's say we start from the 0th guy. You try to place queen in every possible way here, and for every possible way here, you try every possible way here. Similarly, for every total possible combinations of these 2, you try to place queen in every possible way here, so on and so forth. So I'll give you a concrete example. Let's say we have a 4x4 chessboard here. Fine. So we initially start with the 0th column. How many options do you have to place a queen? You have 4 possible options. What are those 4 options? I'll show you. 1, 2, 3, 4. I hope you can see it. Yeah, you can see it. So for the 0th column, so initially we start with the 0th column. So if we start with the 0th column, how many options do we have? We start with the 0th column. How many options do we have? We have 4 options, right? There are 4 possible rows where you can place it. So you can either place it in the 0th row, you can either place it in the first row, you can either place it in the second row, or you can place it in the third row. Now for every possible choice you made, so there were 4 choices here, right? For every possible choice you made, so there were 4 possible choices, try to, now the column of your choice is the first column, first column, first column. For every possible choice you made for the 0th column, try every possible combination for the first column, right? So I guess this is making sense slowly and steadily, right? For every possible combination in the 0th column, try every possible combination in the first column. Let's try to expand them. I may not be able to expand every one of them because I'll be left out of space, but I'll see. Let's just go step by step and see how many we can expand. Otherwise, the rest you will have to do it as an exercise. Fine. Let's start with this chessboard. Now, for if you place the queen on the 0, 0 cell, where can you place the queen? So let me zoom in a bit here. Fine. So what are your options? Can you place a queen here? No, you cannot place a queen here because this queen will directly attack. Can you place a queen here? No, you cannot place a queen because this queen will attack. So where can you not place the queen, by the way? You cannot place the queen where this first queen attacks. So this queen attacks here, here. So yeah, only these 2 cells you cannot place a queen. So you can place a queen here and here. So there are 2 possible branches here. So I'll duplicate it again. This. Right, so there are 2 possible places where you can place the queen. So the first queen was here. Now, so for the 0th column, if you place the queen on the 0th row, next time when you go to the first column, you can either place a queen here or here. So you can either place a queen here or here, right? So the if you place the queen for the 0th row of the 0th column, next time when you go and consider the first column, you have 2 options: either place it on the 2nd row or 3rd row. So these are the 2 options here. Fine. Let's come to here also. So if you had placed the queen on the first row, that is index 1 row of the 0th column, what options do you have? You cannot place a queen here, here or here, right? So this queen attacks like this, but you can place a queen here. So you only have one option. You only have one option. Fine. You only have one option. So there was already a queen here, but now you can only place a queen here. Rest of the places this queen attacks, right? So this queen attacks here, here or here. So that's one thing. Fine. Okay. Similarly here, let's see, this queen attacks here, here, here. So you only have one possible option here. Cool. Let's do the same. Fine. Okay. So there was already a queen. There was already a queen on the 2nd row. You cannot place here, here, here. So you only have one option. You can only place a queen here. Fine. So effectively, this I leave as an exercise to you. This again, you can say there will be. You cannot place a queen here, here. Yeah. So you can place a queen here. So I'll not write it here because I'm out of space. But this you can assume it will also span, right? So what is this? The combinations here will be when you have placed queen on the 3rd cell, you can say 3rd row of the first column, and yeah, so 3rd row of the first cell, right? All the combination here will be when you place the queen on the 3rd row equals to 3 of the 0th column, right? So this will be all the combinations here. Fine. So let's see here. So what happens afterwards? So these are all the combinations you can say where you have placed so this will actually consider all the possible options if you have just placed queens on the first 2 columns of your n by n chessboard. So what next then? Now you have placed queens on the first 2 columns. Now try considering the 2nd column. 2nd column, right? So this combination will be there as well. And yeah. So now what options do you have for the 2nd column here? Let's see one more because otherwise this is getting, I guess, bit too longer, but I guess you are getting the recursion here. What you are trying to do, you are trying to place queen for every possible row on the 0th column, then you are trying to place a queen for every possible row of the 2nd column, right? And so on and so forth you go. Let's explore one of these paths so that we can actually get a valid placement. And I do know behind the scene that this is going to lead to a valid placement. Okay, so you're going to believe me, or you can just trace all of them because I am running low on space here. And so yeah, let's explore this one. So now we are considering the second column. Can I place a queen here? Can I place a queen here? No, I cannot. This will attack. Can I place a queen here? No, this will attack. Can I place a queen here? No, this will attack. But I can definitely place a queen here. So let's try to do that. Let me bring out a chessboard. Fine. So we only had one option. So these two were already there. For the 0th column, we had made a choice. For the first column, we had made a choice. And now we placed a queen here. Now you have to make a choice for the third column. Now what options do we have? See, in reality, we had 4 possible options, but we have to choose one which is safe. That is, none of these 3 are attacking. Can I place a queen here? No, this will attack. Can I place a queen here? No, this will attack. Can I place a queen here? No, this will attack. There is only one place where I can place here. So this queen won't be attacked by anyone. So let's do that. Let me zoom in a bit. Yeah. So we already had a queen. We already had a queen here. We already had a queen here, here, and now only one place was remaining, and now we have considered all the possible columns. So you can say if there was some variable which was tracking this, let's just C. So now C has become 4. So this you can say is a stop condition of a recursion. So this is where you can say the recursion will stop, right? This you can already see that a recursion function is happening here, right? So you are making 4 choices, and depending on what choice you made here, you are again making some choices. Fine, so this will stop, and this you get a valid placement. So here you can maybe just update, you can say a count variable that you might be having, plus plus. So if that C has become 4, that is the current column has become N, effectively you have placed all the possible 4 queens. Now also let's trace one of the path which may not lead us anywhere. So what will happen then? Let's see. Which one should I pick? Let's pick one which help us with the most space. Let's try to explore this path and hope it doesn't lead to anywhere. Let's see what are our options. Can I place a queen here? No, I cannot place a queen here. Can I place a queen here? Yes, I can place a queen here, right? So this queen, no, I cannot place a queen here because this queen will be attacked by this one. Can I place a queen here? No, this queen will attack. Can I place a queen here? No, this queen will attack. So in a way, there is no possible way, right? So there is no possible way. So this column pointer, like this column index variable, won't move further. So you won't update my answer. The answer won't be incremented. Fine. So the answer will only be incremented. You have considered all the possible columns. So can you write the pseudocode here? I think we are in a position to write the pseudocode. So what does our function do is, so our function actually takes, you can say, the chessboard we have, right? It takes the chessboard, the entire n by n chessboard we have, and it also takes the current column we are in, right? And what it tries to do is it tries to put a queen on every possible row. So R goes from 0 till you can say n minus 1, right? So it's 0. It tries to place a queen on every possible row. That's what it does. Now if it is safe, so I'll come to this safe part. If it is safe to put queen on our board RC, what you can do is you can actually put it, right? So if it is safe, you can put a queen on board RC like this, right? And then what you can do is you can consider moving ahead, right? C plus 1. So what it says is try to place a queen in every possible position in the 0th column. Once you placed it, yeah, register it that this queen is placed, and then go and find out all the possible ways of putting queen on the first column, so on and so forth. When you come back, that is, once you've considered all the possible ways after put the queen on this row of the 0th column, you have to backtrack. That is, you have to reset. This to the earlier part. You can say the empty part, right? The dot was representing empty, right? So this, I guess, step might be confusing, but it should not be. This is a classical backtracking step. So what it says is for the 0th column, you had 4 possible options, right? So once you place a queen here, try every possible combination here. When you come back, before you put a queen here, you have to clear this, right? Once you have considered all the possible paths here, and you come back and before you place a queen here, you have to clear this. So that's what this step is, right? So for this column, try to place a queen on every possible row. If it is safe, you put it. If it's safe, you put it. Then go and find all the, you can say, move the next column and repeat. And this is backtracking. Fine. And what is the base condition then? The base condition is pretty straightforward. If this column has equal to become n, you can just increment your answer plus plus. Right. So if you have reached here, then you can increment the count. So you have, if C has become equal to n, it means you are able to place all the possible n queens. Now all that remains is to figure this part out. How do you figure out whether it is safe to put a queen? So this condition, let's see. How can I place a queen? Let's say we have a function is safe, which takes in the board, the chessboard we have n by n, and takes R and C, which actually defines the cell that we have to check whether it is placed to see whether it is safe to place the queen or not, and returns true if it is safe, otherwise it returns false. So what I can do is I can just replace this thing with a simple if check, that if it is safe to put the queen on, let's say I'll just pass board here, on the cell defined by R and C, I'm gonna put it and then move forward and then backtracking, right? So that's the function here, right? So it's a complete function. So this is base case, this is the remaining part. So here of course you can return as well, you have to return as well, right, after updating the answer. And yeah, I mean that's about the pseudocode, and all that remains is to figure out is safe function. So one thing is very clear, if board of RC is actually equal to star, that is, if it is a reserved cell, you cannot do it, right? So in this case, you will have to return false, right? So if it is a reserved cell, you cannot place a queen on it. Okay, fine. Then what do we need to check? What we need to check is, in the current state of board, whether it is safe to place the queen or not. So let's just try to see how would that logic work out. So what I'm doing is, my algorithm, we are going column by column, and each column we are going row by row. So let's say I am trying to place a queen here. Now I have to check whether the queens that were put earlier than it will attack this queen or not, right? So there, like, our algorithm fills the chessboard, right? So there might be queens before it. So you might argue that Kathan, will have to check 8 possible direction, right? Because a queen can be attacked in attacked from 8 possible direction, right? So these are the 8 possible direction where a queen can be attacked, right? So you might say, okay, we have to check 8 possible direction. However, the way our algorithm works, you can exploit and discard some of the possibilities here. How do you think are we filling the queens? We always go column by column. So if I'm placing a queen here, there won't be any queens on the columns after it. So by default, these options are gone, because there won't be queens after it. There won't be any queens in this area. So why should you consider that part? Similarly, you are placing queens row by row, so there won't be any queen below it, because if you are placing this queen, you are sure there is no queen below it, because it will happen next. That try will happen next. On the same grounds, there will not be any queens before it, because you're not placing more than one queen on a given row or a given column. Fine. So all that remains is to check these 3 places. Where you can definitely have a queen, right? Because you are filling row by row, column by column. So yeah, there might be some queen in this part, which I'll call it as, let's say, upper left diagonal, right? So let's call this path as upper left diagonal, and there might be a queen here, right? There might be a queen here. Let's call it, you can say, left of the same row, and this part as well, there can be a queen. Maybe let's call it as a bottom left diagonal, right? So these are not standard terminologies, I'm just naming it, right? So all we have to check is whether some queens are present here, here, or here, right? Which one is the simplest one? I guess this one is the most simplest one. So what you can do is you can actually initialize a variable here, which we have to go back, right? You will have to start from here and check in the same row whether some queen is present or not. If it is attacking, then we have to return false. So what you can do is you can maybe initialize a variable here, which is j equals to c. So if this was c, this was c, and this was r. So rc defines the cell where you're trying to put the queen, right? So you can initialize j equals to c minus 1, and what you can do is while j is greater than equals to 0, that is we have not gone out of bounds, what you can do is you can check if board of row is same but the column that you're checking has a queen. Like if there is some queen present here, there is some queen present here, because if there is a queen we will be placing it right like this. So if it has a queen, we can return false, right? So if the same in the same row you find a queen, you can return false. Fine. And now let's move on to checking this upper left part. If there is a queen, so upper left means this part. So what is this cell? What is this cell? This cell is r minus 1 and c minus 1. So maybe you can initialize two variables, I equals to r minus 1 and j equals to c minus 1. So now what you can do is you can again run a loop here, right? You can run a loop while what? I greater than equals to 0 and j greater than equals to 0. So why I'm doing that? Because see, first this guy will check, then this guy will check. So we'll have to subtract I and j by 1 on each iteration. If my board of ij has a queen, if my board of ij has a queen, we can return false, right? So we can return false, right? So that you can do. And of course, like here you will have to, this is the case, otherwise you will have to do I minus minus j minus minus. Similarly in this case, of course, this is a loop, right? So then you'll have to do j minus minus. Okay, so that is the thing. So similarly you can write for bottom left as well, right? So bottom left, how do you initialize it? Let's just go there as well. So the first cell in the bottom left diagonal will be what? It is r plus 1 and c minus 1. So I equals to r plus 1, j equals to c minus 1. So here what you'll do is you'll effectively first come here, then here. So r will keep on increasing, right? So here you'll have to write while I is less than n, or you can say 8 in our case, but yeah, till we have gone out of bounds, right? So you'll keep on increasing and eventually go out of bounds. So while I is less than n and j is greater than equals to 0, because now this time j is anyway going back only. J is greater than equals to 0 if board of ij has a queen, you can return false. Otherwise I plus plus j minus minus. Fine. And if none of these three satisfy, like if none of these three will return false, and this one as well, right? So now here you can place the checks for, you can say, left diagonal. You can place check for the left, and you can place check for the bottom left. So this was top left, right? So if you can say false was not returned here, false was not returned in these three places, in the end you can return true, right? So that's our if function. Simple. Check whether there is a reserved cell, check the top left diagonal, right? Check the top left diagonal, check the same row, or check the bottom left diagonal. I guess these are very simple loops. That's why I didn't feel like I should go too deep into it. But yeah, I mean, that's about this. And the pseudocode is done and dusted. Now all that remains is, so like this is a complete fine pseudocode and it can be converted to working code. I hope you understood the explanation, like the recursive approach till now, and the pseudocode as well. If you did, please comment understood. And now let's analyze the time complexity, because that would be very interesting. So what happens is, like, how do you analyze the time complexity here? In recursion based question, there are two important terms that you will hear a lot, which is called depth of the recursion tree, like depth of the recursion tree, and branching factor. So what is branching factor is, at a given level, in the worst case, how many branches you will span, and depth will be the total depth of this recursion tree. Now in this case, what you are doing is, let's first figure out the depth. What you're doing is you're filling column by column, right? So in the worst case, the depth can go as high as, you will first be at 0th column, then will be first column, then will be at second column, then third column, and there will be a column made for fourth column. So depth will be as high as 4 in this case, or you can say n. The depth will be n. What is the branching factor? Branching factor means how many of these branches are spanning here. Now in the worst case, you can say there will be, you can place all the 4 possible queens, right? So if there was no this configuration of attacking and all, constraints of attacking and all, the branching factor could be as high as 4, right? Because you could place queens in any of the possible rows. So branching factor can also be n. So if the depth is n and the branching factor is n, the time complexity, you can say the number of calls, right? The number of calls turns out to be order of n power n. So that is just a rule of how recursion tree works here. So this is a rule. If the depth is n and branching factor is n, the number of calls that will be made will be order of n power n. Fine. And so these are number of calls, and how much work do you do at every call? You just try to place a queen and you call our isSafe function, right? So this isSafe function you call. isSafe function, what is the time complexity here? So this is just a constant time operation here, right? So this is just constant time. This and this, these are what you do is effectively, in the worst case, your queen, you're trying to place a queen here, so you'll have to check this. So it can be as high as order of n. So the total calls made are order of n power n, and in the worst case, you might do order of n work. So this is the total time complexity, order of n into n power n. This might look a very humongous complexity, but since n is very small, this will work. I'll show you the exact number, but it turns out to be somewhere around 1E7. So this very well fits within the time constraint. So that's time complexity. And what is the space complexity then? We'll be storing this states of chessboard, right? Of course, at a time only one of these will be used, right? So like this is gonna call this is gonna call this, so on and so forth. So definitely space is used here, right? So what is the space? You are using a n by n chessboard. And in the worst case, what can happen is the space complexity, if I'm talking about space complexity, it is order of n into n for sure, right? And what we are doing is effectively we are passing the same chessboard, right? So this chessboard will be passed to this function, this chessboard will be passed to this function, so on and so forth. So yeah, time complexity is simply order of, space complexity is simply order of n into n, but that's only one more space, which is induced by this depth of recursion tree, because this will call this will call this, so on and so forth, right? So it can be as high as order of n. So space complexity for chessboard, which is n into n plus order of n for auxiliary stack. So that's about time and space complexity. And yeah, I mean, let's move to the code part then, which will be very simple. All right, let's understand the code now then. I'll take the board here. So of course I have solved it for now 8x8 chessboard. So vector string of size 8. So these are, you can say, a board of I will represent the current row of the chessboard. Then I'll initialize this variable count. What is this count is? This is my answer variable. So what I'll do is I'll pass this count as a reference to this recursive function, and we'll update it whenever the base condition is hit. That is, we have considered all the possible columns. We have placed queens in all the possible columns. And this is the starting column we have. So this is what I'm going to pass. So inherently, this is what we need most, board and call. So this, you can have a global variable, but I'm passing it as a reference. And let's see this count placement function. This is a recursive function. See, what it does is base condition will come to it, but what it tries to do is it tries to place queen on each row of the current column, right? For row equals to 0 till 8, we'll check if it is safe to place a queen. I'm going to place it and then move to the next column. And this is classical backtracking, right? And let's check this is safe as well. Then is safe is simply, if it is a reserved cell, false. Upper left diagonal, if there is a queen existing, return false. Left side of the current row, return false. If it is a bottom left diagonal, you return false. If you have not returned false any of these cases, then of course it is safe. Just place it. Fine. So that's that. And the base condition is, if you have placed in every possible column, you will call the function for c equals to 8, or you can say c equals to n. So in this case, you can just increment your answer. So that's about this. Then what is the time complexity? N into n power n. So 8 into 8 power 8, which actually turns out to be this number 1.3 into 1.3 E7. And you know that in 1 second, you can run about 1E8 number of operations, right? So yeah, and space complexity is simply order of 64, that's 18 to 8. So that's about this question. I hope you liked it. If you did, please give it a thumbs up. I'll see you in the next one.